No, it's fine.
Okay, guys. So very happy to have lecture 3 and 4 from Balázs on rings and projective geometry. Thanks a lot, Balázs.
Yeah, thank you. Thanks for coming back. So let's just recall the setup. So I'm going to now kind of start from this very precise algebraic point and state some general results. So we have some ring in polynomial ring in a finite number of generators, commutative polynomial ring, and we have this positively graded. So the degree of each variable is some positive integer. So the degree of di xi equals wi is some positive integer, and so this then becomes a non-negatively graded connective ring. So degree infinity as d and s0 is k. So this is a finitely generated free graded commutative k algebra. Positively graded connective. Okay. So now we've decorated it with all the objectives we need. So that's our S. And then I is some homogeneous ideal. Here, homogeneous. And then we have R is the quotient ring. And because we are working in an Noetherian ring, this is generated by a finite number of homogeneous elements. Okay, so that's our setup. And for a while, I won't emphasize the geometric side, but remember, we had a geometric side, and on the geometric side, we have the vanishing locus of this ideal inside a weighted projective space WPN or Pn Wi, and this was a quotient of a to the n plus 1 minus 0 modulo a star with weights W0 W. So that's the geometric story. So this is our X, and this is proj of R, and this guy is proj of S. Okay, but for now I'm just going to focus on the algebra. So notice that now we can have so the degree of the Fi is going to be some di. Homogeneous. These live in some homogeneous degrees. And so notice then that we can write a little piece of a sequence. So we have S surjects onto S mod I. So the kernel here is, of course, I. I want to build a complex of S modules, free S modules. So this starts like this. So I have a surjection from S to S mod I. So this is surjective. And then, so the kernel here is I, but I want to, I is not a free module, so I want to replace it by a bunch of free modules. So I want to map to the generator. So inside here lives I, and I is generated by F1 up to Fk. So what you can do is you can take a direct sum of copies of S, and I'm going to put shifts there, so shifted by some di, just to be consistent with the gradings. I think I put square brackets last time, so I want to put square brackets again. So this is just a shifted free S module. So here I have as many as the variables, and then here the map is and a multiplication by. So if I think of this as just a module map, then I'm just multiplying each copy by Fi and then add them up, add up the different copies. So that's sort of the starting point of a resolution. So this is then at this place. This is now exact. So this surjects onto the kernel, and then the kernel gets quotiented out. So this piece of a complex of S modules is very natural. And basically all we are saying here is we are encoding the generators of this ideal into this module map, into this map of free modules. I mean, this is a very standard thing in module theory. And so that's how it begins. And then there is this, and I won't always say it, but I want minimality. So I want a minimal set of generators here. So these are not going to be unique, but there is there's a choice of a minimal set of generators. So I don't want redundant generators. If some generator is already generated, throw it out. I don't need that. So minimal just in that sense, that no subset generates the ideal. And then this is a sort of minimal start of a sort of sequence. Now, so the example is a hypersurface case. So if actually I is principal is generated by a single element, the principal ideal, then we are more or less done. Because what happens is, so f in degree d, then you start the sequence, you go SD, goes to S mod F, goes to 0, and this is just multiplication by F in this case, and multiplication by F is injected, right? Now we have a free ring or free algebra. There is no kernel here. Multiplication by F, there's no kernel whatsoever. So actually, this is an exact sequence. This is a short exact sequence. Sorry, in this case. So this is a short exact sequence of S modules. But if you kind of like homological algebra, then another way to think about this is that here I have a complex of free S modules, and that's quasi-isomorphic to this ring that we are trying to understand. So that's a kind of different way of saying this. There's always these 2 points of view. I can either build a resolution of, so this is just our R in this case, so we are resolving R by free S modules, or I can say that there's a complex of free S modules which is quasi-isomorphic in the sense of homological algebra. It's just equivalent. So this is the example. So in this case, we are done. But if you have more equations, then this is not going to be injective, of course, because we are mapping from a higher rank module. And so here is then Hilbert's syzygy theorem. So theorem, this is a big sort of starting result in the subject. This is the G theorem. Is that you can always resolve any ideal of this. So there's a homological finiteness here, so you can resolve any ideal. So there exists an exact resolution of this R, which is S mod I, of the form. Okay, so we need some notation. So the last piece is always S, and then that surjects to S mod I, goes to 0, and then there's a first step. So direct sum S di, and I'm going to say di1. So these are just the equations. So this is just f1 up to fk. But then there's going to be some other things. So there's going to be some direct sum S of dj2. It's kind of hard to get all the indices there, but so there's going to be some number of these. So the I1 goes from 1 to some k1, and then the j2 goes from 1 to k2, and so on. And then there is this is finite. So there's going to be a last one. So there's going to be some finite, some direct sum S of the k L, and then the j, and then the KL goes from 1 to, I've lost my indices, I'm sorry, JL, that should be a JL, and the JL goes from 1 to KL, and that's 0. So it stops in a finite number of steps. So there's some kind of length. So there are L steps here, and then the situation stops. Okay, so that's the theorem. So even though you can't get away with just a one-step thing, there's going to be some modules to add. Well, the theorem says that after a finite number of steps, you've built a resolution. And I'll give examples in a minute, but the reason, so this first step, as we've seen, this is where the generators of the ideal sit. in the second step, if you think about it, so this surjects onto the kernel of this map. So these are relations between the generators. And then these are some kind of higher relations. And these higher relations are called syzygies. These are the G's of the generators of I. So that's the interpretation of this. So we are building some free complex of S modules. And this is going to encode basically the structure of the generators, the relations between the generators, the relations between the relations of the generators, and so on. And the key fact here is this finiteness. So basically, if you think about it, building such a thing is kind of essentially trivial. You have a map. You have in every step you have a Noetherian situation. So you have a finitely generated kernel. But the key thing is that it stops also after finitely many steps. So that's the non-trivial part of this statement. So that's this exact resolution. That is a finite exact resolution. Okay. And once you know that, then this actually has a very simple corollary, which really is just a telescope principle. The corollary says that the Hilbert function, I think I called PR of t, has the following form. It has a numerator and a denominator. So in the denominator, we have this expression that we saw before. So this is the weights of the generators are included in the numerator, in the denominator. And then in the numerator, you're going to have, okay, so this is, I'm going to try and write this. So this is the sum J equals, I need a new letter, M equals 0 to L. Then there is a -1 to the M. And then there is a sum J equals 1 to Km T to the D M J. Okay, I'll give examples in a second. But so basically, you just feed these numbers with alternating signs into your polynomial, and that's the answer. And this is basically, once you unpack it, this is a very easy statement. So all this is saying, you want to compute graded dimensions here. This is an exact sequence. There are some shifts. So these are the shifts, and this was the. So down here, of course, we have the Hilbert function of just S itself. Maybe I write this down separately. So one trivial example of this, of course, is when I equals 0, R equals S, and this resolution is just 0 goes to S, goes to S, goes to 0. And so the resolution, I mean, this is the R part, and then this is the S part. It's 3 already, and then PS of t is just, we only have the M equals 0 term. So this is just 1 over the product of 1 minus t to the wi. So that's one example.
Those d's are coming from the resolution, eh?
These are coming from the resolution. Maybe I'll give one or two other slightly less trivial examples, and now you're beginning to see how this thing works. So this is kind of example 0.
I just mean that the only information we take, I mean, not just in this example.
Well, for this, no. So a very good question. So in general, of course, we're going to be super interested in these maps also.
Okay.
No, absolutely.
But as far as the Hilbert function is the only
thing. As far as the Hilbert function is concerned, because you're just telescoping the whole thing together, you don't see that.
You only see the d's.
Yeah, I mean, it's the same thing as, Euler characteristic is the sum of the alternating sums of any chain complex resolving, blah, blah. So this is just a graded Euler characteristic. Okay? It's just a graded Euler characteristic of my ring, and I'm getting it from a free resolution, and that collapses plus or minus, you just do the usual trick of homological algebra. And yes, but I mean, that's a very good point. Of course, to understand the ring itself, we very much want the maps also, very much want some understanding of the maps. And And again, I'll give some examples. But as far as the Hilbert function is concerned, that's just numerical information. This is the graded Euler characteristic. So the graded Euler characteristic doesn't mind the maps. So that's kind of example 0, and then example 1 is here, and we've seen that before. So if I have just a one-step resolution, that formula will say that the Hilbert function of R of t is 1 minus t to the d over the product of 1 minus t to wi, and we've seen that formula last time. So if I have a hypersurface, one equation, then that's the Hilbert function. And again, you just take degree d, or degree e is the same as degree e of this complex, suitably interpreted, and then you just get this. So let me give sort of the first non-trivial example, so going beyond hypersurfaces, so example 2. Suppose I take two polynomials, f and g in S of degrees d and e, so homogeneous. I want two homogeneous elements. Then I can build the following complex. So S goes to S mod. So my ideal is going to be the ideal generated by f and g. So these are my minimal generators. And then there is an S d plus S e. And the map here is fg. So I take two elements, kind of matrix multiply. Then I'm going to do 0 goes to S b plus e. And then g minus f. So what's the point here? So the point here is, if I have some polynomial h here, that will map to gh minus fh. And these guys are certainly going to be the kernel of the next map. So the next map goes kl goes to fk plus gl. Okay, so these are the maps here. And somehow trivially, these things are in the kernel of this map. And so here is a little lemma. So this is obviously injective, this is obviously surjective. So the only issue is this really a resolution? So the question is, have I built a resolution? And the lemma says that this star is exact in the middle. If and only if G is not a zero divisor in S mod F. And in particular, if F is irreducible, then it's enough to say that this is still a domain. So then actually anyway, this is the condition. Sorry, this is a condition. It's non-symmetric, but actually this is symmetric. So this is also if and only if F is a non-zero divisor in S mod G. So this is just a little calculation. You just want to show that, want to check, is this complex exact in the middle, and that this condition just comes out very naturally. So in this case, and we'll give a general definition, but this condition star, which is equivalent, so we say that star means that F and G form a regular sequence. So I mentioned that word last time already. This is some kind of genericity assumption. And so if F and G form a regular sequence, then this is a resolution. And this is the resolution claimed by Hilbert's syzygy theorem. And in this case, it's basically saying that our two equations are F and G, and the only relation between our equations is the obvious one, that G times F equals F times G. So that equation you're always going to have, right? I have two generators. I map them by F and G. How can they be related? Well, if I multiply something by G and something by minus F, obviously they are going to give me something in the kernel. And so this condition, this genericity assumption says that that's the only relation. So this condition can be translated into this algebraic statement or different algebraic statement that the only relation between F and G is the trivial one. Okay, so in this case, what happens? So So in this case, we get that the Hilbert function of this ring is, well, I can read it off from here, 1 minus t to the, let's look at the formula. I have a minus sign for m equals 1, t to the d, minus t to the e, plus t to the d plus c, over the product of the 1 minus t to the wi. So that's just reading it off, but this factors. So this is just 1 minus t to the e, and 1 minus t to the d, over the product of 1 minus t to the w. And this is a typical situation for these regular sequence cases. That actually, in these regular sequence cases, you're always going to have a factorizable denominator and the factorizable numerator. And that's a hallmark. I mean, these are never equivalent conditions, but if you have a regular sequence situation, then your Hilbert function is going to show up like this. And one other comment I wanted to make, which is going to be interesting in a minute, is that you can interpret this complex in sort of in the theory of like in homological algebraic terms as just as a tensor product of two complexes. So the one in a suitable sense is literally just a tensor product of these two complexes.
So, Bash, can you use a non-ready pen?
Yes, sorry.
Okay.
So if you suitably interpret it, if I take these two complexes, so the one for f, I take the tensor product in the category of complexes, then you just get this. So this is the same. So the statement is that if I have a regular sequence, or if and only if this tensor product of complexes remains an exact complex apart from its last piece, if and only if this algebraic condition holds. And if it holds, then you get this factorization. So this is that tensor product statement is equivalent to this guy factorizing here. And this now has a generalization. So you can now do this in more elements. Coming with chemical weapons, thank you. Thank you. Okay, so generalization. Suppose I take a bunch of elements. So suppose I take my k elements, so f1 up to fk, homogeneous elements of S of degree bi, then I can do the same thing. I can take these elementary complexes and I can just take a big tensor product. So I don't want to write it out. If you write it out, then this will be, so what is it going to look like? So it's going to have, so how do we take a tensor product to complexes? Literally, you just use the distributive law, and you take your higher powers further to the left. So this is going to end in S. Then its first step is going to be exactly this direct sum of S di. That's its first step, multiplying. So it's exactly the same thing as what I had before. And then it's going to have some kind of direct sum S di plus dj, and then and so on. I don't want to introduce a whole lot of new notation for this, but if you tensor product these together, and at the very far end, and that will be important, there's going to be a single copy of S in degree sum wi, and then whatever else is happening. Okay, now this is called a Koszul complex. This is a Koszul complex of the elements f1 up to fk. of our ring S. So the Cauchy complex comes up in many different areas of maths, and this is the only one I know, but they're all very similar constructions. So you can interpret these in terms of certain wedges. I mean, and this is a kind of tensor product with signs, right? So there's going to be some, so maybe wedge product is a, this is what it is, tensor product. Tensor product with signs. And so, okay, so that's a complex. It certainly resolves at the end. So it is true that there is a map from here to S mod I. That's okay. But the question is this a resolution? And then this is the theorem about the Cauchy complex. So the theorem says that this is a resolution of S mod I. So I exact everywhere except, well, exact everywhere if I write it like this. So exact in all places before. If I only live, these elements form a regular sequence. Up to Fk form a regular sequence. And so what is, and the definition of that is inductive in the same way. So F2 is not zero divisor in S mod F1. F3 not a zero divisor in S mod F2, and so on. And Fk is not a zero divisor in S mod F1, Fk minus 1.
Balázs?
Yes.
So if we have that the fraction of polynomials over there,
Yes.
can we recover the exact sequence?
No, not completely. So I'll give examples. So this is a very similar question to what Bruce asked. This fraction is only the Hilbert function. So no, in general not, but it gives you a lot of information. But in general, you will not be able to fully recover the exact sequence. So what's the game here? The game is, maybe you have some numerical information about some ring, and you build its Hilbert function, and then typically it will come out to be in some kind of format. I'll give you some more examples, but the simplest possible format is the one that I'm going to write down, the factorizable one. And then you say, okay, it looks like an intersection, it looks like it's generated by some elements of these degrees in such a ring. And then you still have to show that that's going to work. So one of the purposes of this whole project, as I said at the very beginning, is to construct new examples of varieties. And how do you do that? Well, you build a database of possible invariants. You get possible Hilbert functions. The Hilbert functions will suggest a certain way of constructing these varieties, but you still have to construct them. So I'm not sure, I mean, I'll give some examples, I think, in the second hour, but I won't get to the details of that. But no, so this is a very crude information about the ring, the Hilbert function. But sometimes it's still enough for us to be able to guess or even prove that it has to have a certain type. So, so this is this algebraic condition of being a regular sequence. I mean, this is going to come a couple of times. I mean, so for this, I can give some kind of justification in a minute. But you know, there's a lot of algebra here, which at first sight you just have to believe that this is the right condition. But then one plays with examples, and then one sees lots of nice examples in action. So,
excuse me.
Yes.
The Cauchy complex. If you permute the f's, is it?
I was just going to say that. So in the graded situation, that is actually true. In the local situation, so there's always a local story and a graded story. In local rings, this is false. In local rings, if you permute a regular sequence, it may not be regular. But in the graded case, this is a not entirely trivial theorem that actually, well, it follows from what I've written. But yes, in the graded case, the permutation of regular sequence is also regular. But this is not. This needs. If I just give the definition, this is not obvious, and it's not true for local rings, but it is true for graded rings. Yeah, good question. Okay, and kind of if this is so a corollary, if I generated by a regular sequence, then the Hilbert function be S mod I T. Well, I can write it both in a factorized form and the written out form, but let me just write it in the factorized form. So the product I goes from 1 to k, 1 minus t to the di. So these are the degrees of the equations, and then product j equals 0 to n, 1 minus t to the wi. So these are the weights of the variables. And this is precisely a kind of Hilbert function description of what happens under this tensor product. The Hilbert function simply multiplies. So let me actually give a couple of examples of this. So maybe what's happening geometrically?
So just quickly, what is the DRs again?
The DIs are the degrees of the Fs,
Okay.
and the WRs are the degrees of the variables. So it's like this. So here, there's one equation of degree d. These are the variables. There were two equations of degree d. So here, but maybe I didn't. Somewhere I wrote the Hilbert function. Maybe it's gone now. No,
but if y is like, if I've got a variable y that's of degree 2, then the polynomial.
Yeah. So that's gonna be here.
But I just want to just make sure I understand.
Mm-hmm.
Then say I've got a variable that's called x of degree 2.
Yes.
Then let's take the polynomial x squared. That's counted as degree 2 or 4?
4.
It's counted as degree 4. Okay.
I'll do some very explicit examples in a minute, and you'll see that. But yeah, that's right. So everything is counted here with S is graded with these weights. Yeah. So remember, we had this ring K.
Like a linear function,
degree
20.
1, degree 2, degree 3.
Yeah.
And what is the degree 6 piece of this? That was generated by x to the 6 and y squared and z cubed, zy cubed and z squared, sorry, and whatever else, x, y, z, a bunch of other things, right? These are the degree 6 polynomials in these variables. So this is degree 6 because it's 6 times 1. This is degree 3 because it's. We always count with this natural degree. So let me just say what a regular sequence says geometrically. So if, I mean, this is an if and only if, so F1, Fk form a regular sequence, if and only if X is the intersection of these hypersurfaces, I equals 1 to K, is of codimension K. In other words, geometrically, what we're saying is that we take equations and every equation cuts down a dimension. So in the linear case, this is something that we study. So how many linear equations do we need to define a subspace? Well, as many as it's codimension, but as long as they're linearly independent. And this is the same thing here. So geometrically, what we are doing is, if in a regular sequence case, is we are taking these new equations, and every time you take a new equation, you cut down the dimension. That's the meaning of this non-zero divisor business. So, so geometrically, this is somehow a very natural notion that we take hypersurfaces, we intersect them, and we get sort of one more condition. And so codimension K here means that the dimension of this weighted projective space is n. And then the codimension of X is n minus the dimension of X as an algebraic variety that has some definition. And so we are saying that this is exactly the number of equations. So this is a very general, this is a very kind of natural thing to say, that I take K equations and it cut me down every time I intersect it cut me down in dimension. So that's the geometric meaning. And I mean, it happens sometimes. Many varieties are not complete intersection varieties, but many interesting varieties are. And so from the point of view of this theory, that's sort of the least interesting case, because the resolution is just a Koszul resolution, the Hilbert function is trivial, and I mean, there's still some interest in constructing them, but this is somehow the least interesting case. So this theory is trying to understand cases which are not complete intersections. So go beyond this relatively straightforward case of complete intersections. Well, let me give one example from a slightly different subject, which would be a start of another talk. So I will give it, of course, but just to show you that you have seen these things before. So let me take just a polynomial ring with degree 1. And just for now, I'm relabeling, so I'm just going from 1 to n. So each of the degrees is 1. So this is the straightforward case. And then, yes?
Could you give an example of a variety in which you cannot choose a regular sequence?
I'll give 1 second, okay? Yes.
Thank you.
This is an example where it is, and now I'll give it one where it isn't. Let EI be the ith elementary symmetric polynomial. Symmetric polynomial. So, you know what they are. E1 is the sum of the xi's. E2 is the double sum. J, and so on, and En is the product. And so let I be the ideal generated by the elementary symmetric polynomials. And so the claim is that these do form a regular sequence. So the claim is the set of variables E1 up to En. So these are all homogeneous, right? So this is homogeneous of degree 1, degree 2, degree n. So claim E1 up to the n form a regular sequence. I won't prove that, but it's not difficult. But as a corollary, so if I take S mod I is a finite dimensional. This is this codimension business. We started projectively in codimension n-1. I took n equations. I got to essentially codimension n, so dimension -1. This is a finite dimensional K algebra with Hilbert function well, we can just read it off now. The Hilbert function is PR, so this is R, PR of t is product 1 minus t to the I over 1 minus t to the n, I equals 1 to n. So this is p n factorial. So it's the factorial, it's the nt, sorry, it's the p number factorial. And in particular, it's a finite dimensional K algebra of dimension n factorial. And this is a super interesting algebra. So as I say, it's the start of a different talk. It carries a representation of the symmetric group. As a representation, it's a regular representation, but it's a graded representation. It's a starting point of a whole book on symmetric functions. Okay, so this is one example of some very nice algebra with a very nice Hilbert function coming from a regular sequence, and it's big. So this is Stanley's, or this is called a Cohen-Variant algebra. This is the name, the Cohen-Variant algebra. And this was studied by Stanley and many others. Lustig, Stanley, lots of people studied it. So that's just one example. Okay, so let's see another example. So actually, I'm gonna play the numerical game that I've played before. Yeah, it's the usual thing. Sorry, I should not use it. Chemical warfare. Yeah, thanks a lot. So we'll approach this ring in different ways, but let me kind of start with the mystery point of view. So an interesting example is a ring R times some R. I, where the dimension of Ri, Rd is 3D plus 1. So, okay, so I've given you the dimension, so we can build the Hilbert function. I won't do it by hand, but the Hilbert function of this ring. So this is some, I goes from 0 to infinity, 3D plus 1, t to the d. Okay, you get Mathematica or your analysis tutorial or whatever, and then you go away and compute, and this is turning out to be 1 minus yeah, 1 minus 3t squared plus 2p cubed over 1 minus t. I didn't sum it in my head. I was remembering where I'm heading. So this is a true statement, I hope. Okay, so immediately you can see that this is not a product. So this doesn't factorize. So this is something else. This is right. So this cannot come from a complete intersection because this is polynomial. It factorizes a bit. So you could cancel. So it actually, and there's a reason I'm writing it like this. But 1, and then what is it? 1 plus. So you can cancel one thing, but I have it written down somewhere. Sorry, I'm not. Yeah, so this is t equals 1 as a root. I'm sorry, 1. I thought I can swing this. I've written this down so many times, but I still can't.
Plus t squared, 1 plus t squared, 1 plus t minus 2t squared?
Yeah, that's right. So actually there's another factor here and then just 1 plus 2. Yeah. So what happens here? So what happens here is this is not of this complete intersection form. Okay, so this is not of the form, this is not of this form. And so what can we see here? The simplest possible way, and remember, we had that formula for the resolution and so on. The simplest possible way we could get this, so the simplest possible resolution that might be compatible with this is the following. We take a polynomial ring generated by 4 variables. I mean, that we know because the dimension of R1 is 4. And remember, I told you that R1 cannot be generated from anywhere. So our oracle told me that I'm starting with 4 variables of degree 1. So that's something we know. And then we say, okay, so that's the 4 variables in degree 1. And now I see this nice alternating sign pattern. So this is compatible with, remember, that formula up there, the corollary, right? We have these alternating signs between pluses and minuses as we build the resolution. And the simplest possible thing that could happen here is there is 3 copies of S2 going to S mod. There's 3 generators here, F1, F2, F3. And then there is 2 copies. So here I equals 1 to 3, and here I equals 1 to 2. 2 copies of S3, and then objective. So this is a possible resolution type. Once again, how did I guess that? I can say this is the smallest possible way that this function could look. 4 variables of degree 1, and then 3 equations of degree 2, and then 2 syzygies of degree 3. This is the simplest possible thing that could occur. And indeed, there is such a ring. So such a ring exists. And we can describe it both in geometry and algebra. So in geometry, this is the example of the 3rd Veronese embedding of P1 into P3. So this is x naught x1 goes to I should use different letters. Y naught y1 goes to y naught cubed, y naught squared y1, y1 squared y naught, y1 cubed. So this is a explicit embedding of the projective line. And so if this is the x naught, x1, x2, x3, then indeed the corresponding ideal, so let's see in P3 be the image of this Veronese embedding, then the ideal of this curve is generated, and this is a computation that's a frequent homework in algebraic geometry, x naught x3 minus x1 x2, and then x naught x2 minus x1 squared, and x1 x3 minus x2 squared, three variables, three equations of degree 2. And these are the guys that come here. So this is the f1, the f2, and the f3. So these are the f1, f2. And this is a standard example. This is the first example of every algebraic geometry course of something that's not a complete intersection. It's codimension 2, so you would expect two equations to define it, but you cannot define this in two equations. This ideal cannot be generated by two elements. It can only be generated by three elements, which have two relations between them. So that's the smallest case where something like this happens. And we knew something had to happen because this didn't completely factorize, and this is an example where this happens.
The three functions is one relation between them.
Actually, there are two. There are two relations, so it's a nice, fun game to work out. This is what Miles Reid calls solving a Sudoku puzzle. So it's like solving a Sudoku puzzle. You want to find, and you know they're linear, so they're degree 3, so these guys are actually linear. So here there is a 2 by 3 matrix of linear elements, Lij. And you can find, in fact, this is going to be true. So this is actually what's called a determinantal or a matrix variety, because I can write this also as the equations as the rank of the matrix x0, x1, x1, x2, x1, x2, x2, x3, if that's equal to 1. These are the same equations, and so then you can play with this in the pub. This is the kind of thing that you can play in the pub, but there's going to be two relations. There are two linear relations between f1, f2, and f3. And algebraically, actually, this ring is the following, and that's exactly the same description. So this R is nothing but, I take the standard polynomial ring, RD is nothing but the standard polynomial ring in y0 and y1, but I only take every 3D piece. So this is what's called the Veronese subring. That's an equivalent description. So I take every third piece of my ring. So that's clearly a subring of, this is a graded subring of K, y0, y1. So this is called the Veronese construction. In ring theory, So I take every third piece, and that's where this 3D plus 1 comes from. The dimension of this is 3D plus 1. And these guys are precisely the degree 1 generators. This y0 cube, y0 square, y1. These are the generators of the third piece of this ring. So this is how these things fit together. Okay. Yeah, so I said people have already disappeared. So maybe let's have a 5-minute break, or shall I just carry on, or I don't know.
No. 10-minute break for coffee.
10-minute break for coffee. I'll do some more examples.
At the very least.
So these are some of the first examples. We'll do some more examples. Yeah, 10-minute break.
Equations like they look like those ones in functions. Those are not like generating functions.
Which one? Polynomials.
Yeah, the polynomials.
It could be, but they probably have a negative here. They could be the generating functions of partitions. The polynomials.
Well, I mean, that would be an infinitely generated ring. I mean, these are always finite products.
Exactly.
Yeah, that's a more interesting situation where you have these are always finite. If you write it in this factorized form, I mean, they're power series, but if you write them in factorized form, then they're finite products. Yeah, so something more complicated like like partitions or planar partitions or whatnot, that's an infinite. But that is just, I mean, that particular thing is just it's just a way of symmetric functions. So that's an infinitely generated by sure functions in every degree. That's one in every degree. So that there is a graded ring there also, but it's not finitely generated. So it doesn't quite fit into this framework. But it's very similar.
I'm going to have to go.
Yes.
Good to see you.
We'll be in touch.
We'll be in touch. Unfortunately, I cannot go this year, but maybe next year when I take a sabbatical, I'll probably come.
Yeah, let's. And if you do, let me know, and I will try and make.
Yeah, definitely.
All right. Just think ahead of time. Okay. Regards to your family.
Thank you.
Thank you for the illicit goods that you transported to me.
Enjoy.
Yeah, I mean, this is the definition. I mean, in some cases that the characterization, I'm sure, but
Somebody else defined and it will happen. Yeah. It doesn't matter what type.
Quite a bit better.
if you please. Maybe you just need to replace the player. No, I mean, there's some kind of trick. Anyway, this is good.
This office doesn't like me.
Okay. Let's go. So I'll do a few more examples, and I think maybe there'll be a couple of general things, and then we'll wrap up. So, so here's a very nice series of examples that I absolutely love, and I wanted to explain. And I started that already, but I'm going to continue. So the example is, oh, no red, sorry. The example is a series of rings related to coming from elliptic curves. So I do want to start with a genus 1 curve and the point. So this is a smooth curve genus 1, and then the P is a point on the curve. And I want to fix some D. Oh, D is going to be fix some, what's the letter? And for fix natural number, I want to take the divisor, which is L times P. So this is in the Picard group. This is a divisor on the curve. And I want to take my graded ring to be with global sections on the curve of D times this divisor, being greater or equal to 0. So this is so these are holomorphic sections on this genus 1 curve, which have a pole of some order, but there is now a further parameter L here. So we discussed the case L equals 1.
So L subscript P, eh? So it was a.
No, L is a number. L is some number, right? Yeah. So this is, before we had L equals 1, yeah. But now we're going to have arbitrary L.
What is L subscript P?
No, L times P.
L times P.
L number, so P is a point, L times P is a divisor on the curve.
But it is the one associated to P, obviously. It's literally P plus P plus P.
P plus P plus P plus P times, and then I'm going to take it D times also. So this is D times L. And so the Riemann-Roch theorem says that the dimension of this space of sections is either 1, if D is equal to 0, or it's L times D, if D is greater than 0. And so this ring is, okay, two by two. I mean, this ring is indexed by this integer L. And so we have seen R1. So R1 is isomorphic to this ring, and this ring, you can spot that on the Hilbert function, but here you really can actually prove these isomorphisms. So this was this ring, 1, 2, 3, degrees 1, 2, 3, modulo some Sachs-Lie polynomial, which we could write as z cubed minus y squared, z squared minus y cubed, plus some degree 6 polynomial of x and y. And we wrote it as plus a x to the 4 y plus bx to the 6. Minus, doesn't matter. So that was R1. And the corresponding Hilbert function corresponds to some 1 plus some d greater or equal to 0, d to the d times d. And we wrote this down. This is 1 minus t to the 6 over 1 minus t squared, 1 minus t cubed. So this is a nice hypersurface example, an equation of degree 6 in variables 1, 2, 3. So this is a projective curve, and this is a nice elliptic curve. So this is L equals 1. For L equals 2, I think I stated this also. So the Hilbert series is 1 plus some d to the d times 2d, d greater or equal to 1, sorry. So if you compute this, then you get 1 minus t to the 4 over 1 minus t squared, 1 minus t squared. And then this ring R2 is isomorphic to k x1, x2, y modulo y squared minus f4 xi. So this is a general degree 4 polynomial after a little change of variables. And maybe I should say also the geometry. So here the elliptic curve sits inside weighted projective space 1, 2, 3. And I think we discussed this a little bit here. The elliptic curve sits inside weighted projective space 1, 1, 2. And here we can see this double cover very explicitly. So I can map from here to P1. It's going to be surjective, branched over the roots of this polynomial f4. So when you have double root, you have a double root. If this is 0, then you have y equals 0. And that's a geometric description of the double cover of the elliptic curve branched over 4 points. Double cover of P1 branched over 4 points. We also looked at R3. So R3 is actually going to be a polynomial ring generated in degree 1, modulo a cubic. So this is like the simplest kind of, this is the elliptic curve we know. So so this corresponds to some 1 plus some 3 d t to the d, d greater or equal to 1 equals 1 minus t cubed over 1 minus t cubed. And the geometry here is just that the cubic curve in P2, arbitrary cubic, given by F3. Okay, so these are all, well, maybe the top one is the least familiar model of an elliptic curve. The next one and this one are more familiar. What is R4? So L equals 4. L equals 3. L equals 4. So we have 1 plus some t to the d times 4d, d greater or equal to 1. And the answer here is 1 minus t squared over 1 minus t to the 4. Compute it if you don't believe me. And so what's the geometry here? So this is also quite a familiar thing. So this looks like a complete intersection. Okay, so we have 4 generators of degree 1. So here we have the ring R4 is going to be k x0, x1, x2, x3 modulo a regular sequence of 2 quadrics. So Q1, Q2, This is the intersection of two quadrics in P3. So the elliptic curve is Q1 equals Q2 equals 0 inside P3. The intersection of two quadrics, and if you know the, not going to talk much about the canonical class, but if you know the adjunction formula, the canonical class of such a complete intersection is the canonical class of P3 plus 4 copies of the hyperplane section, but the canonical class of P3 is negative 4 times the hyperplane section. So this is trivial canonical class. Anyway, this is the adjunction formula. Restricted to B. And this is 0 because the canonical class of P3 is minus 4 times the hyperplane section. So this is a trivial canonical class. Trivial canonical class for a curve means that it's minus 1 elliptic curve. So this again is a very standard. So these are the so-called standard models of elliptic curves. Plane cubic or the intersection of two quadrics in P3. So this was known to, I don't know, people like Jacobi, that you can build elliptic curves or one-dimensional tori in this way. And then L equals 5 is really interesting. So what happens at L equals 5 is the following. So the answer is 1 plus some d to the d times 5d, d greater or equal to 1. This will turn out to be the following: 1 minus 5t squared plus 5t cubed minus t to the 5th divided by product 1 minus t plus 1 minus t to the 5th. Okay, so that's the answer. So what is this? So this will factor a little bit like our other example did before. I can't remember exactly. I don't want to write something wrong, but this polynomial will not factor completely. So this has a one factor of 1 minus t, probably 2, but after that it will be an irreducible polynomial. So this is not a complete intersection model. So here we get the elliptic curve sitting inside P4, and you see the codimension is getting bigger and bigger. So in these geometric models, so this is a hypersurface. This is a hypersurface. These are still hypersurfaces. So is this. This is a complete intersection. This is codimension 2. The elliptic curve sits inside P3. The one-dimensional variety sits inside P3. Now the one-dimensional variety sits inside P4. So the codimension is getting bigger. So this is codimension 3. And so what happens in this story is that that somehow the difficulty increases as the codimension goes up. So as you get bigger and bigger codimension, you get more and more interesting rings. In codimension 1, that's the Hauptidalsatz that you can only get a hypersurface. So codimension 1, we only have one polynomial. Codimension 2, we have already seen an example which is not a complete intersection because we had P1 in P3. So remark, we had P1 in P3. This was codimension 2 and not a complete intersection. There is a reason for that, which I may or may not get to, but here we have a codimension 3 guy, and this is also not a complete intersection. And the story here is really getting quite interesting. So this is still a very classical question, and the very classical question is: suppose you take an elliptic curve and embed it by some Veronese truncation of its natural ring, what sort of embeddings do you get? And so people studied this question classically. So this is not really new discoveries. This is still very classical constructions being interpreted in a slightly different way. So let me explain the geometry here. So what is the geometry here?
Just the background here. So the idea of weighted projective space is a fairly newish idea of what?
Well, 1970s, 80s.
But it's not before then. So
it's not before then. People, but okay.
Yeah.
Let me come back to this question. Okay. And I need to remember the numbers, but I think, yeah. Well, let me give you an example in a second of that. Okay, so let me just finish the geometry. So what's the geometry here? So what is the geometry of an elliptic curve embedded by the 5 times Veronese truncated ring inside P4? And so that turns out to be super interesting, and it's the following. So we will get this model, we will get, so what information do we have? If everything works well, then we will get this as follows. We have that the elliptic curve is given by 5 quadrics. Q1 equals Q5 equals 0 inside P4. These are quadrics, suitably chosen quadrics. Now, for general quadrics, you will not get an elliptic curve, but some special quadrics. And then there's 5 generators, and then 5 syzygies, and then one of these higher syzygies. And this is in codimension 3. And so the next key idea here, and again, the name is Miles Reid's. I mean, this is not necessarily a brand new idea, is to think about some things that he calls key varieties. So key varieties are special varieties. I don't want to often homogeneous, so these are often homogeneous spaces that allow interesting constructions of rings by hyperplane section, by taking hyperplane sections. And I should say, so this is the way I write it is Miles Reid, but also Macaulay did a lot of work realizing certain varieties using this kind of principle. So this is both Miles Reid and Macaulay have used it very successfully. So, I mean, again, I'm going to be very naive about this, and I say, does anyone know a ring of this form? So what do I want? So I want some variety V inside some projective space, Pn, of codimension 3, and given by 5 quadrics. 5 quadrics. So of course, this is a kind of very naive rhetorical question, because I mean, the answer is going to be yes, and I'm going to pull out a rabbit from a hat. But this is pretty much how this happens. One is looking around for interesting varieties and interesting ways to change it, and then get new constructions. So what is the answer here? So the answer here is a very classical construction. This variety is the Grassmannian Groth5. Really the first interesting variety, first interesting Grassmannian. So this is the space of all planes in a 5-dimensional vector space. So this is like projective space, but we don't do lines in a vector space, we do planes in a vector space. So this is a Grassmannian of planes in K5. So this is some projective variety. It's a GL5 modulo a parabolic. So there's some description of this as a symmetric space. Anyway, there are also descriptions. You open some book on algebraic geometry, and there's going to be some description. But in particular, there is an embedding called the Plücker embedding of any Grassmannian. Plücker, which in this particular case maps to P9. So there is some kind of numerology of where you map these matrices. So here you map it to a certain space of 2 by 5 matrices, a space of, the space of 2 by 5 matrices. That space is 10-dimensional, but we projectivize, so this is 9-dimensional. And this variety, again, you look up your book, and it's a 6-dimensional variety. So the Plücker embedding is an embedding of some very nice symmetric space, this Grassmannian, into P9, and it's got this property that it's codimension 3. And you continue looking at your book, and the ideal of the Grassmannian, again, I seem to like red, sorry. The ideal of the Grassmannian is generated by 5 quadrics called the Plucker quadrics, Plucker coordinates, generated by, sorry, the Plucker quadrics, on the Plucker coordinates, of which in this particular case, here there are 5. So once again, what happens here? What happens is there's some special variety. This embeds into P9, and it's got the right resolution structure. So, okay, let me write it as a theorem. The embedding V equals greater to 5 into P9 is an embedding of codimension 3. And the corresponding, so if I equals the ideal of this variety, then P S mod IV is 1 minus phi t squared plus 5t cubed minus t to the 5th over 1 minus t to the 10. So here we are embedding into P9, but so I have 10 variables. So this is kind of what I expect. And so this is a non-trivial result. I mean, there's something to prove here. I'm not, this is getting more complicated algebraic geometry, but this corresponds to the 5 quadrics. And then this corresponds to 5 syzygies, and then higher syzygies. So this is kind of what we expected from this setup. So that's the first half of the theorem. And then what is the second half? If you take a generic P4, then you get the following situation. So taking generic 4-dimensional subspace, we get this P9 inside this generic 4-dimensional subspace P4. Here I have V, and then here I have the intersection P4, and this is our elliptic curve. So this is the embedding that we are studying. So you can get this embedding by taking this higher dimensional variety and then cut it down just by linear subspace. So these are generic 4-dimensional subspaces.
Sorry, I've completely lost what happened on this board now.
Okay, where? Which one? Okay, so I'm saying I want to find this elliptic curve somewhere naturally in geometry.
That elliptic curve right there. Okay, good.
That elliptic curve, right?
Okay.
I'm saying, what do I know about it? It's codimension 3, and it seems to be wanting to be generated by an ideal if generated by 5 quadrics. Do I know such a variety? Well, I sit next to Miles Reid, then I do. I mean, this is classical stuff. One such variety is a 6-dimensional variety under its Plucker embedding into P9. That has the right resolution structure, but it's too big. So I'm going to chop it down. So if I chop it down, what I'm saying is here's some very, very special variety in P9. So this is a pretty rigid setup. Now I'm going to take a 4-dimensional linear subspace, some 4-dimensional linear subspace. And then if I intersect it with the general 4-dimensional linear subspace by V by Bertini, the codimension is not going to change. So this is codimension 3. This is codimension 3. And so this is a curve, because it's in a 4-dimensional space and it's a curve.
Yeah.
And I'm telling you.
So it's the shadow of the Grassmannian.
Well, it's a linear section of the Grassmannian. It's a linear section. So it's like saying that the conic section is a section of the conic. Instead of the conic, I'm taking this Grassmannian. And instead of taking a plane, I'm taking a 4-dimensional subspace inside a 9-dimensional space. And any such is going to be an elliptic curve. And once again, there is some calculation that if you take that this is just going to be right, that the canonical cost of this right is going to be trivial. And this is a complete intersection. So here we are taking, so this means I take 5 linear equations. So that part is really a complete intersection. So if you want, 5 linear equations means that I multiply this by 1 minus t to the 5. So that's going to be the thing I want. That's going to be this guy. So this is a geometric story where we build this elliptic curve inside this ring, inside this Grassmannian, or using this ring, but something which doesn't have, it's not a complete intersection anymore. So this Grassmannian is not a complete intersection. The Grassmannian is some homogeneous variety in P9. It's defined by 5 equations. And it's exactly the same as the Veronese. So the Veronese would be another example.
But nothing in this story requires the use of weighted projective space.
Not here,
Yeah.
not here. Let me give you a different example, and I haven't prepared that example, so I won't give you the full picture, but let me give you a sense of another problem.
Lucas,
Yeah.
The word generic means that you are ensuring you intersect the variety.
That it intersects properly. I mean, if I take sections of a conic, here generic would mean avoid the vertex. If I go through the vertex, then I get a union of 2 lines. I want a non-singular situation. I want a smooth situation. So if I take a generic linear section, I get a nice conic section. But if I happen to go through here, then I might get a union of lines or something. Or if I'm a tangent, then I've got something even worse. So I just want a non-singular situation.
Is it too hard to give an idea of the definition of generic?
Well, here it's general. There is some space of linear equations, and I just want a Zariski open subset of that space of linear equations. Now, what exactly the conditions are, that's probably a bit harder to say. But generic in this situation means I have a parameter space of. What is this parameter space? It's another Grassmannian, right? The space of these in these is a Gr 510. Okay, so everything is so a 4-dimensional linear subspace of P9 is a 5-dimensional subspace of a 10-dimensional space. So that's another Grassmannian. So if the parameter space of these guys in here is this, and I'm just saying that I take a certain Zariski open subset of them. But it's exactly the same here. I just want planes intersecting my cone, but those planes that don't go through the origin.
Yeah, there I see.
Yeah, here but it's the same kind of thing. You certainly don't want something which creates singularities. It's very easy, but we already have that. Look, if I say hypersurface, vanishing locus to that hypersurface inside Pn, I again mean generic hypersurface. I want a non-singular hypersurface. So here it's possible to say what is non-singular. I don't want gradient f equals 0 to have any solutions. So that you can describe in terms of some discriminant. That's always a technical question, and sometimes it's not so easy to answer. But there is something called Bertini theorem, and the Bertini theorem will say that if they are general enough, that for a Zariski open subset of all the parameters, you're going to have a non-singular variety. So that's the kind of thing. So here one can be completely explicit. Here that you want to avoid the discriminant hypersurface in the space of parameters. Okay, so let's try and answer Bruce's question. As I said, I haven't prepared the numbers, so I won't be able to give you the exact numbers. But one type of problem, suppose, elliptic curves is kind of silly because we don't really want to classify elliptic curves. We know what elliptic curves are. So in a sense, these are all just kind of thought exercises for the method. But somewhere where you really want to construct varieties is the following. So suppose S is a non-singular surface of general type. And maybe let's make the assumption that as a sub case, so let's actually assume that Ks is ample. So the canonical class is an ample divisor. Most of them will be ample. There are going to be some cases where it's not ample, but general type is implied by ample. Let me not worry too much about. So associated to this, there is a ring. It's the same definition. I take direct sum of the global sections over S of D times the canonical line bundle. D equals 0 to infinity. Now these are not classified. surfaces of general type with ample canonical divisor are not classified, so we don't know what, I mean, many examples are known, but we don't know all the examples. I mean, in some sense, we never will, but even the small ones are. So there are two invariants. One is the self-intersection of the canonical class, ks squared, so this is some natural number, and then the geometric genus PG, which is just a dimension of the first of this canonical class. And let me actually see somewhere in my notes I actually have the formula. It's going to be embarrassing that I won't be able to do off the top of my head the Riemann-Roch for surfaces, but I won't. I think I have it somewhere written down. Anyway, there is some. So from these two invariants, there is the Riemann-Roch theorem will tell you the dimension of these rings. So the dimension of the space of sections of Ks. So this is again going to be 1 if t is equal to 0, and we are just taking the trivial bundle. And then there is some formula in terms of Ks squared and Pg, which I don't remember. But if we sit in a pub again, we can. There's some very simple formula. You just plug this into Riemann-Roch, and there's some formula in terms of Ks squared and Pg. So from here, you can build the Hilbert function. R. And it will have some form. And I'm not going to go through the whole process, but I'll give you some ideas of what are the kinds of things that could happen here. So one possibility is, and there are various subtleties here which I'm not saying much. So one possibility is you get the function, so you start with Ks squared equals 5 and Pg equals 3. And then you go through the process, you follow the formula, which I can't remember, go through the process, and you discover that the Hilbert function PR of t is 1 minus t to the 5th over 1 minus t to 4. So I hope I'm not lying if this doesn't start the right way. So this should start 1 plus 3t plus higher order terms. If it doesn't, then I'm lying, because PG, that's the first coefficient. But I think this is right. 4. PG equals 4, and that should be 4. And then there is one known example. One example here is quite easy. One example is I just take a quintic hypersurface in P3. So this is codimension 1, so this is a surface. That's 2, so it's that doesn't mean the sphere, so it's not notation. But S was already not good notation because I had an S before. But anyway, this surface is a surface of general type. So Ks is OS minus 4 plus 5. So this is OS of 1. So this is ample, in fact, very ample in this case. So okay, so this is a trivial surface of general type. The quintic surface in P3 is a surface of general type, and it's not such an interesting example. We know it. We don't need graded ring methods to construct it. But there's another example which is just a little different. Another example is the following. So I take, I'll fill this in ks squared equals, k squared equals 1, pg is 2. So you go through the method, and then you get that the ring still looks quite, sorry, at least the Hilbert function still looks quite nice. It goes 1 minus t to the 10 over 1 minus t squared, 1 minus t squared, 1 minus t to the 5th. So now beginning to see these higher weights. And so this looks like a degree 10 hypersurface, at 10 in some variables x0, x1, y, and z equals 0 inside weighted projective space 1, 1, 2, 5. So I'm just literally reading of the 1, the 1, the 2, the 5, the 10, if it exists. If everything works out, then there should be a variety like that. And there is, and everything here works out. So this is a weighted projective space. There is some adjunction formula which says that the canonical class is OS minus 1, minus 1, minus 2, minus 5, plus 10. Probably don't have time to explain this, but this is OS of 1. And despite these weights, this is actually a non-singular hypersurface. Non-singular, the general one. So once again, the general degree 10 polynomial will give you a non-singular hypersurface in this weighted projective space. Okay, so is this a new variety? So it turns out that this variety was known to Enriquez in the early 1900s, but he didn't have weighted projective space. So how did he think about this? So this is not really new.
Well, one second. Well, one thing I don't understand about algebraic geometry.
Yeah.
Right? If you sort of said, is this a new variety? Is it wow? We're on the look. We're trying to construct
Trying
varieties.
to classify, yeah. Algebraic geometry half the time wants to classify
Well,
varieties.
I can just go down, just write down some polynomials. I say, there, I've made a variety.
Yes.
What is special about you?
Yes. So what? Very good. So what is special here is there's going to be a lot of constraints. In particular, this is a singular variety. This variety. So I mean, this is kind of the next lecture. I won't really have time, but this is actually a singular variety. You started out saying I want to construct non-singular surfaces of general type. So it's actually a non-trivial fact that the numbers worked out. So the key fact here is that this 10 is divisible by 2 and 5. That means that actually this is the general variety is non-singular, but it works out so that the canonical class is O of 1. So there's actually a lot of constraints. So this is another part of this Sudoku puzzle, that you're trying to fit different numbers together, and in many cases there are going to be finitely many solutions. So so there's a lot of things that are hidden here. If you actually start doing it, if you write down some numbers, then probably you wrote down something garbage.
You're trying to construct varieties with.
You're trying to construct interesting varieties which are non-singular or close to non-singular. I mean, no one cares about very highly singular varieties. Or I mean, to give you a stupid example, suppose you wanted to write down, okay, I want a cubic hypersurface in weighted projective space 167. I mean, this is absolutely bollocks, because I can't find a cubic polynomial in these variables that's anything other than x cubed equals 0. That's not going to be a very interesting variety, right? So if you start writing down stupid numbers, then you're not going to get anything, okay? So this x6 in P123, that had the same property. That actually this 6 was divisible by the 1, the 2, and the 3, and that made this elliptic curve non-singular. So I'm kind of hiding these technicalities under the carpet, but if you just throw some random numbers at me, then you probably define some kind of garbage variety, not a nice variety. But this is a nice variety, and I'm saying that this was known to Enriquez. So how did Enriquez think about this? So here we have this x sitting inside this weighted projective space 1, 1, 2, 5. And incidentally, PG equals 2 is just the fact that there are two variables of degree 1. This is x10. So what is the equation? So we can play the same game as in the Weierstrass normal form. So this is x0, x1, y and z, then this will be, after a little change of variables, this will be given by z squared equals f10 of x0, x1, y. So now I can forget the z coordinate, and I can project to weighted projective space 1, 1, 2, and I have a double cover. Now, this is still a singular variety. That's still a singular variety. So this is a double cover branched over f10 equals 0. But actually, this variety was known to NITheCS. So actually, this variety has a different description as the quadric cone in P3. Again, let me not explain this. This goes, but that actually NITheCS knew this variety. That's actually quadric cone in P3. So NITheCS would have described this variety as a double cover of the quadric cone branched over with a branch locus, which is the cone point, near a degree 10 curve. So he has some other way of describing this. So there are some of these varieties will turn out to be varieties that actually the classical geometers described in some way, but it's much more clumsy. So this is a much more compact description of this variety. But you have to have some new language. I mean, it's the usual thing. We have an old description, which is maybe a little clumsy. If there's new language, then you might get a better description. And this is one of these cases. So this is part of an NITheCS classification of certain types of surfaces of general type, and this was known more than 100 years ago. But you can sort of rediscover it as part of this machinery of building gradient rings. So as you can see, I could go on forever. I think I'll give one more example and then we stop. Okay, how about that? So here is another example which just shows the last, on this level where we are, the last kind of interesting possibility or a kind of bifurcation. I will actually cheat because I want to do this properly with the right numbers. So let me actually try and find this in my notes somewhere. Yeah. So suppose I have a smooth curve and its canonical divisor. So this is genus 3, and I want the degree of the canonical divisor. Then it's going to be, so this is 2g minus 2, so this is 4. This is just kind of basic algebraic geometry. So this is the canonical divisor, and it is always ample. Canonical divisor is always ample on a curve of genus greater than 1. And then, okay, so I want to take the ring, which is once again, the global section ring of the canonical divisor, d times kc, d greater or equal to 0. And I want to understand the structure, and I want to understand proj of r. So proj of r is going to be embedded in some projective space or weighted projective space, and I want to understand this embedding. I want to find my curve as embedded in some projective space. So again, this is a very well-known example, but we'll see an interesting kind of dichotomy. So now I open my Riemann-Roch, and my Riemann-Roch is going to say that the dimension of the space of sections on C of d times the canonical class is 1 minus g plus a degree, and the degree is 4d. If d is greater or equal to 1, or it's 1 if d is equal to 0, and so this is 4d minus 2, because the genus is because the genus is 3. Okay, so I have these numbers. So the Hilbert function of the ring goes 1 plus t equals 1. I have 2t plus 6t squared plus 10t cubed plus 14t to the 4 plus. Okay, so that's the Hilbert function. Maybe I have to do, sorry, I don't think it's slightly wrong here. Sorry, that's still not right. So this is when d is greater or equal to 2. And, okay, you have to do the Riemann-Roch calculation. For d equals 1, you have 3 sections. I'm sorry. So this is actually a 3. Because the negative term, the other term still contributes. Okay, that's what Riemann-Roch does. Sorry. And then you say, okay, so what is this ring? So here I have 3 generators in degree 1. That's for sure. I must have x0, x1, x2. And then here I can see the 6. So S2 of these SIs, so this is 6-dimensional. So if they are linearly independent, if there's no quadratic relation in my ring, then I have then I have exactly the right number of quadrics. S3 of xi is 10-dimensional. This is just this basic formulae, binomial coefficients. So maybe there's no cubic relation, so I've got the ring covered. And then S4 of xi is 15-dimensional. But here I only see 14, so there must be a quartic relation. So this is a story. I told you a story, but to check the story, you can actually sum up the series, and indeed, the answer is 1 minus t to the 4 over 1 minus t. So this is like consistent with my story that I have 3 generators in degree 1 and a quartic relation. And indeed, one possible model for this variety, so x equals proj r, one possibility is indeed that it is a quartic curve in B2. So this is the general genus 3 curve. A general genus 3 curve is a quartic in B2. This is a plane curve, degree 4, genus b minus 2, b minus 1 over 2. So this is 3. Okay, so this is a very well-known geometric situation, and this is part of a course on algebraic curves. So this is the next example. So cubic curves are elliptic, and quartic curves are genus 3. So that's very good. But we made an assumption, and actually there is now an exception to this assumption. So the assumption was that if this is 6-dimensional and they are linearly independent in the ring. So that's an assumption. If this is satisfied, then you get this curve. But actually, for this Hilbert function, there's actually another solution. And the reason there is another solution is that the Hilbert function is not, this product form is not uniquely defined. So I can write the same Hilbert function. I can write the same function that I have there, PRT. I can write in the form 1 minus t squared, 1 minus t to the 4, divided by 1 minus t cubed times 1 minus t squared. Okay, I did something silly. I just put in a 1 minus t squared both in the numerator and the denominator. But there is a case where this happens. So let's go through it one more time. So in degree 1, I have x0, x1, x2. In degree 2, let's assume that I have a quadric relation. So I have x to xi modulo some quadric, and then I need a new generator. And then it turns out that you go through, then you get to the same conclusion that in degree 4, there's going to be a new relation of degree 4. And so what is the algebra here? So in this case, and this is in this case, the R is generated by x0, x1, x2, y. So these are degree 1, 1, 1, 2. Modulo this quadric relation Q only involving x0, x1, and x2, and some quartic relation. And that quartic relation, as we had this trick before, I can complete the square and just write it as y squared minus some quartic in polynomials.
What's the difference in a quadric and a quartic?
So this is a quadric in the x-size, this is a quartic in the x-size, but then y squared is also degree 4.
What the word quadric and the word quartic?
Quartic is in the 4. Quadric is 2. Quarto is 4.
Quadratic is 2.
Quadratic is 2 and quartic is 4.
Okay.
I'm sorry, yes.
Okay.
This is degree 2, degree 4. Quartet is when 4 people are playing with. And what is the geometry here? So I'll just finish with this geometry. So the geometry in this case is I have this variety in weighted projective space 1, 1, 1, 2, given by 2 equations, some second order equation of x at 0 and z squared is f4. But once again, I can do this trick of projecting down to P2, so just the first 3 coordinates. And if I project the x, then I'm going to have this equation that goes away. Sorry, y squared. So this is x0, x1, x2, y. This equation goes away because I've projected out y, but I still have a quadric in x0, x1, x2 equals 0 inside here. And what is this? Well, a quadric in P2, quadric plane curve is a rational curve. So this is isomorphic to P1. And now how many? So this is ramified over F4, so this is ramified over 8 points. And these are hyperelliptic curves. So this is the hyperelliptic case. So this is the geometry of what's called hyperelliptic curves. Double covers of P2 branched over a certain number of points. So here, what did I call it? X or C? Sorry, C. So here the C is a hyperelliptic curve. So say C is hyperelliptic. So this is a situation that can happen, and you see it in the graded ring. The graded ring differentiates between plane quartics and hyperelliptics, and this is again a very classical result in curve theory, that in the moduli space of curves of genus 3, you have plane quartics and you have hyperelliptic curves. These are the 2 possibilities, and you see that here appearing on the level of the ring theory.
So you mean this is an example of what Fano was saying, so that, yeah, you've got the Hilbert polynomial doesn't distinguish them.
Doesn't distinguish.
But the algebra does.
Right. So they have the same Hilbert polynomial, right? If I cover it up, I can't make a difference. But what's happening here is that here you have a relation and then you have a new variable. And it's kind of very pretty because you can even see the degeneration of a plane cubic to a hyperelliptic curve. Because I could have this quadratic equation, this Q2 could be Q2 of x0, x1, x2 plus lambda times y. And for lambda non-zero, actually I can eliminate y. I can just y, I don't really need y is minus 1 over lambda times Q2. So I don't really need it in the ring. But if lambda equals 0, I cannot eliminate it. So then I get the hyperelliptic. So if I take a family of curves with this equation plus a quartic, then at lambda non-zero I have a plane quartic, and at lambda equals 0 I have a hyperelliptic curve. So this happens in the moduli space of curves. So you can begin to study moduli spaces of varieties by varying these ring constructions. I think that's a good place to stop.
Okay, so firstly, thank you so much, Balázs, for these amazing lectures you've given. I think let's have some questions now for the talk, and then we'll let everybody go, and if people want to stay longer can ask more questions at the board. So, any questions now?
I have one. If you have a Hilbert function, are there always finitely many varieties that, or
yeah, very good question. And finitely many families of varieties. And yes, so this, at least under some assumptions, but yes, the assumptions I want to make is going to be true. So yes, there is something called the Hilbert scheme. So if you take a certain Hilbert function, you take a projective space, and you take all possible subschemes of projective space with a certain Hilbert function, those form a bounded family. Yes. But in general, to say how many components does it have, or what is its geometry, that's very difficult. But yes, there is finiteness here, and that follows from this Grothendieck's general definition of the Hilbert scheme. So to every Hilbert polynomial, there is some certain subscheme of certain parameter space parametrizing subschemes of projective space with that Hilbert polynomial, and that's a finite variety. It sits in some Grassmann. So yes, there's always finitely many, but you have no idea how many. Okay. In general, it's hard to describe.
So it's not the sort of thing that you can stuff in a computer.
No, people are doing that. So there is a group in the UK. People around Kropczyk and Tom Coates and Gavin Brown and people like that. They have now hit this all with machine learning. So because you can generate Hilbert functions, and you can generate interesting Hilbert functions, and you can try and actually learn. So they now have a database of thousands of varieties, and they have hit it with kernel methods and machine learning. Early days, quite what we are learning, but they get some. They are now putting out papers with some really cool pictures of like the density, and so this is called the geography of varieties. You say, I fix some numerical invariants, and I want to understand, are there varieties with these numerical invariants, how many there are, and what. So they have now built, so for example, they have now built a large database of Fano varieties, Fano threefolds, and they're learning from that database of Fano threefolds, and they're trying to
write the names on the board.
So this is people like, so it's kind of Imperial, and then various other people attached to that. So okay, so there's a slightly different stories, but like Gavin Brown is one of them, and then Tom Coates, and then Kropczyk, I can't write that. Okay, I'll always have to look up. All if you're listening, I'm sorry. It's a long Polish name with lots of consonants, and I never remember what exactly goes in there. And yeah, I mean, these are the main protagonists. So Al and Gavin, I mean, these people have now, they're running little meetings of machine learning and algebraic geometry in the UK. So that's a bit of a theme. I mean, it's related to mirror symmetry. It's related to classifying. So classifying Q finals. That's the catchphrase. So there's a paper from about a year or two ago about exactly that with some subset of these authors with machine learning. So yes, they are now trying to. So there's something earlier. So the thing earlier is called the GRDB, Graded Ring Database. So that's the source. I mean, Gavin Brown has been building the graded ring database for 20 years. And it now has polytopes and toric varieties and this type of varieties, that kind of Q-Fanos, surfaces of general type. It's a very big database now, where you can enter some parameters of the Hilbert function, it will build you the Hilbert function, and it will also spit out to you a lot of possible rings that could have that Hilbert function, that kind of thing. So that has been built and for various types of problems, and that is kind of the core data or the raw data. But now that goes into these machine learning methods, and they're trying try and get some kind of patterns. And they really get cool patterns. I don't think anyone understands these patterns, but they now have these big pictures with like swings of like dots in them, and the dots have certain shapes, and it's all cool. So yes, people are studying this now with large scale computing.
Anyone else? Okay, so I suggest we give Balázs one last thanks, and then the people who want to stay and chat to him, we can stay and chat to him.